This video is going to cover the basics of antiderivatives. So we hopefully all know what a derivative is, and you know all the sort of fancy tools we have for taking them, sort of using the algebraic shortcuts, not just the limits. Things like chain rule, power rule, product rule, quotient rule. Antiderivatives is the sort of process of undoing that derivative process. And as you might imagine, undoing the derivative process is much harder than doing the derivative process. So let's dive in a little bit. First, just with a definition. A function capital F is an antiderivative of little f on a particular interval if when you take the derivative of capital F, you get little f. Okay, so this is sort of like if I started with little f, our sort of standard function, I want to go back up a layer, right? Or in other words, if I start at capital F and I go down, I should get to little f. Okay, so let's just do a little bit of antiderivative work here. So you may want to pause and ask yourself, what is a function such that when I take the derivative of that function, I get 2x? Or what is a function such that when I take the derivative of that function, I get sine? So pause if you haven't and think about it. Okay, so if you're back, this just is hopefully, we're able to think about it okay. Like if you take the derivative of x squared, you should get 2x, right? You take the power rule, bring it down. Okay, fine. But also, you may want to ask yourself, is there another one? So again, pause and think about if there's more than one of these. And there is. How about, for instance, x squared plus 5, right? Or x squared plus literally anything I want, right? Because when I take the derivative of a constant, it's going to not matter what it was originally because constants will always disappear. So there's more than one antiderivative, okay? That's why it says an antiderivative, not the antiderivative, although we do have language for the antiderivative coming back up. And what's the derivative for cosine or for sine? You may be tempted to write just cosine, but that's not right because what's the derivative of cosine? It would be negative sine, and we don't see that negative here, which means we need to counteract it by adding an extra negative here, right? And again, there's nothing that says you can't add literally any constant you want, like let's say plus pi, for example, because that pi would disappear when I take the derivative. Okay, so this is the general idea of what an antiderivative is. It's a function that when you take its derivative, you get your original function. Okay, fine. Well, here's a quick theorem that says that if you have any antiderivative, like plus 3 or plus 7 or whatever, every other antiderivative is of the form f plus c. So basically what that says is there's no antiderivative for 2x that doesn't use x squared, right? There's no antiderivative for sine that doesn't use negative cosine. Okay, the only way you get more than one of these things is by sort of just doing this cheap trick, or like add a constant, add 10, 10 is your constant or whatever. But the sort of meat of the antiderivative is always going to be the same for every antiderivative of a given function. So that's what this theorem says. And we'll also just go ahead and introduce this, what's called an integral symbol. It's this elongated S. And when you see an elongated S, this integral symbol, it always gets paired with a differential. Hopefully you're familiar with differentials. So this says take the antiderivative of this function with respect to the variable x, right? So differentials are often pointers to the variable. So specifically, it's telling you take the antiderivative with respect to this variable, okay? And in general, we give the sort of meaty part of the antiderivative, and then we throw a generic plus c on there. And what this means when you write this is that if you took the derivative of this side, you would get this little function inside the integral on the other side. And this f of x plus c is called the general antiderivative for your little function, okay? And that is a the, right? Not just a general antiderivative, but the general antiderivative. So let's just go ahead and do a couple for this, where we're supposed to find the general antiderivative. So there's only one answer here, unlike above. So you may want to pause and work on these. Okay, if you're back, you might be sort of thinking about how you should do this, and we know that we're essentially going to have to use the power rule on this to get down to this, and when I use the power rule, I get, I'm going to take down my exponent by 1. So if I had x to the 4th, its derivative would be 4x cubed. So that gives me the x cubed I want, but I'm not supposed to have a 4, so I need to counteract that by introducing a 1/4. And you could check that if I took the derivative of this, right, I would get x cubed. But because I'm looking for the general antiderivative, I'm going to throw a generic constant on here, plus c. And it's sort of a joke in calculus, right, that students forget their plus c. So always remember that plus c should be on there. And again, you may want to pause and try to mimic what we did here for this. And if you're back, this one will be 1/8 x to the 8th. And again, plus c. So we're going to try and use these two to develop something called the power rule for integrals. So if I have x to the nth power, then what's the antiderivative going to be? And again, you might want to pause it and try to answer for yourself. It will be 1 over n plus 1 times x to the n plus 1. Or if you prefer, x to the n plus 1 over n plus 1. You know, it's the same thing if you multiply it out. But you use the power rule on this, right? You'd bring down the n plus 1, which would cancel this, and then you'd subtract 1 from your old exponent, leaving you with an n. Except there is at least one value of n for which this does not work, right? Like if you look at this, when would this not work? And I'll tell you, it's specifically there's one that's a problem. It's when n is -1. If I try to do the integral of x to the negative first power using this rule, I would get 1 over 0 x to the 0th. That's not good, right? 1 over 0, that's not right. So this is obviously incorrect. So what are we going to do in this situation? Well, I want to take the antiderivative of 1 over x. That might look familiar. So can you think of a function, you might want to pause, can you think of a function whose derivative is 1 over x? Okay, so if you're back, let's go ahead and see if we can figure this one out. The integral of 1 over x dx is, you might be tempted to just put natural log of x, but you actually need a slight adjustment. It needs to be the absolute value of x. And the reason you have to have absolute values is because this function 1 over x, its domain, right, is -infinity to 0 and 0 to infinity, which means you need a derivative that makes sense for most of this interval, right? In fact, all of this interval, because when you sort of look at this, it's these sort of smooth pieces of curve, so the derivative should exist for both of these things, right? But the domain for natural log without the absolute values is only things that are strictly greater than 0. But if you put those absolute values on now, 0 is still missing, which is fine because it was missing from the original. But now if you plug in a negative x, you just take the positive version. So you have to have these absolute values, and the reason is because you need the domains to match up, sort of. Because this doesn't make sense for negative x values, but this does. So you have to reconcile that with absolute values. Okay, so now we've got a couple of antiderivative identities here, this power rule, and then we've also got 1 over x. Okay, a couple of the basics. This result is one that I'm not going to belabor, but I wanted to put on the screen. Derivatives sort of play nicely with respect to addition, subtraction, and constant multiplication. And because derivatives are sort of, you can split them up and think about one piece at a time, then it's also true for antiderivatives, that you can split them up and think about them one piece at a time. So that's all this result is saying. And then let's add a few more identities here. So this says basic trig integrals. These may not look all that basic to you, right? Like secant squared, secant times tangent, cosecant, cotangent, right? Like those don't, like why are we not just doing sine, cosine, tangent, secant, cosecant, cotangent? And again, you might pause and ask yourself that question or try to think about it for a moment. The answer is because if we tried to, for instance, take the integral of, let's just choose tangent. Can you think of a function whose derivative is just tangent? I mean, maybe if you're familiar with calculus, you know how to do this, but this is not a straightforward identity. The reason that we have these as our basic identities is because these represent essentially the derivatives of the plane 6 trig functions. So let's go ahead and fill in the gaps here. So you might want to pause and try to figure out which things go in which place, but we're going to go ahead and write through all of these. So antiderivative of sine. So we want a function whose derivative is sine. So that should be cosine plus c, except the derivative of cosine, right, as we discussed earlier, would be negative sine. So we have to adjust by a negative. Derivative of secant squared. That's going to be tangent plus c, right? The derivative of tangent is secant squared. Derivative of secant tangent, that's going to be secant, because the derivative of secant is secant tangent. Derivative of cosine is going to be sine, because the derivative of sine is cosine. Derivative of cosecant squared will be cotangent, except the derivative of cotangent is negative cosecant squared. I don't have that negative in this integral, which means I have to introduce an extra negative to counteract the one that's going to get spit out by the derivative. And then cosecant cotangent is going to be negative cosecant for the same sort of reason. So these may not look like the easiest things in the world, but they're as easy as it gets for trig because they represent they're the sort of what you get when you take the derivative of the 6 plane trig functions. Okay, so here are a bunch more identities to sort of like, these are like our antiderivative building blocks. So using everything that we've talked about in this video, we're now prepared to sort of take the antiderivative of something like this. So this integral symbol, this elongated s paired with the dx, right? This is sort of like capitalizing your first letter and ending with punctuation. Like these always go together. So I can think about these one at a time. So using that result from before, I can split this up and think about these individually. And then I can also factor out constants. So this 3, right, I can bring that out. So really, I'm going to use power rule here and get 1/6 x to the 6th plus some constant. And then I'm going to get 3 times the antiderivative of 1 over x, which is natural log of absolute value of x, plus some constant, which I'm going to call C2. And then derivative of cosecant was negative cotangent plus some constant. So let's clean this up a little bit. So this is 1/6 x to the 6th plus 3 natural log of x minus cotangent x. And then each one of these things is sort of spitting out some unknown constant. But I don't actually need 3 different constants because I don't know anything about what these things are. So if I have generic constant number 1 and generic constant number 2 and generic constant number 3, really I can just think of those as a group. I'll be able to add all those up, right? Combine like terms. So I only really need 1 constant of integration, it's called, right? So when I'm taking antiderivatives, you should only ever have 1 plus c if you're only talking about doing 1 antiderivative, because all the sort of individual pieces can just be combined. There's nothing special about these constants. I don't know what they are. So I'm going to call all of these just c, right? Like whatever that is, that's my constant now, right? So I don't have to sort of show the different pieces. So this is the basics of how antiderivatives works.